Hello and welcome back to Orgo with Rosemary. Today we are going to cover homotopic, heterotopic, enantiotopic, and diastereotopic signals. So let's get started. Before we go into examples of signal counting, I do want to talk about these relationship words. They're very important. The umbrella terms are highlighted in yellow boxes, and they are heterotopic and homotopic. Heterotopic and homotopic are the most general words we're going to use, and before I go into what everything means, I want you guys to be sure that you know we're only going to use these words to compare hydrogens, right? You can't just pick one hydrogen, this one, and just say, yes, this one is homotopic. You have to compare it to something else. And that becomes very important when we look into the nitty-gritty of everything, so I just want to make sure you guys are aware of that. So first things first, we can look at these and pretty much get an idea just with our reading skills about what these mean. Homotopic means that the signals are equivalent. So we only have one signal. Those hydrogens are exactly the same, right? So in this example, it's already written out in words here, but these three hydrogens and these three hydrogens have a plane of symmetry in the middle, so they are exactly the same. We could go even further. I'll label that really quick. So this group and this group, their relationship is homotopic. But we can go a step further and say that within this signal, these two hydrogens, what is their relationship? Homotopic. Because they are exactly the same. So any two hydrogens that are exactly the same are homotopic. Next up is the complete opposite. We have heterotopic. Hetero means different. So heterotopic is a word that we use for any two hydrogens that are completely different from one another. So here I have drawn the same exact molecule, and it does have the plane of symmetry still, but it's not important for us right now. So this purple hydrogen and this pink hydrogen are completely different. These two carbons, one is a CH3, one is a CH2. They're in different places relative to space. Just everything about them is different, so you get two completely different signals. Straightforward enough, simple enough. Enantiotopic and diastereotopic is where it gets a little bit more difficult because these are more specific words and they can only be used in specific cases. First one we're going to cover is enantiotopic, and enantiotopic is used when we have a potential chiral center present. So what do I mean by that? Well, I've highlighted it for you already. A potential chiral center is any carbon that has two unique groups, which we have this methyl and this ethyl, and two hydrogens. The reason we call that a potential chiral center is because, let's say we were substituting HA and HB for a bromine, right? If we were to substitute HA versus HB, the molecules would be chiral now, and one would be the R and one would be the S configuration. The relationship between these two molecules is enantiomers. And enantiomers have the exact same properties. So we are going to have enantiotopic hydrogens that are exactly the same. So if he were to give you HA and HB here and ask you what their relationship is, it is homotopic, but the better word is enantiotopic because that is more specific. On the other hand, diastereotopic is different. So we are going to look at two separate cases where we can have diastereotopic protons. First is with a chiral center, and the second is with a double bond. So first let's focus on the chiral center. As I've indicated here, this carbon is already a chiral center, and on the molecule we have another chiral center. What this means for us is that the two hydrogens on the potential chiral center are going to be diastereotopic. The reason for that is now when we substitute it, instead of getting a pair of enantiomers, we actually get a pair of diastereomers. And this is because now we have two chiral centers. And between these two molecules, this chiral center stays the same, but this one is different between the two. Diastereomers, again, D and D, D for diastereomers, D for difference. These have different chemical properties, and therefore they have different signals on the NMR spectrum as well. So HA and HB right here will count as two separate signals. They are, diastereotopic. The other condition is when we have a double bond. So anytime you see a double bond, I want you to cut it in half long ways, like this. And I want you to just write a number 1 and 2 on each carbon. Doesn't matter which side is 1 and which side is 2 as long as they're labeled. The reason I want to do this is because one of the carbons, in this case carbon 1, should have two different groups, which we have here. We have one methyl and one hydrogen. Carbon 2 should then have two hydrogens. If this is the case, these two hydrogens on carbon 2, again, I'll label them HA and HB, those two will be diastereotopic. And the reason for that is, let's substitute one more time. If we substitute HB versus HA, we get two different molecules, and that is because we do not have free rotation across this double bond. So the configuration we get is the configuration we're stuck with, and they are different. So these two hydrogens are completely different. I do want you to think, however, about what other possibilities we have for our double bonds. So a double bond could also have two equal sides. And if that is the case, if carbon 1 has two identical groups, aka it has symmetry, then HA and HB on carbon 2 are no longer diastereotopic. They're actually going to be homotopic. And the reason they're homotopic is because now there's going to be no difference. There's symmetry. This will be exactly the same. The last condition we're going to talk about for double bonds is, what if we have this? So if we split it in half this time, and we do 1 and 2, there are two completely unique groups and two hydrogens. However, the hydrogens are not on the same carbon. In this case, the relationship between them is just heterotopic. Diastereotopic is a form of heterotopic, but in this last case, it cannot be considered diastereotopic. It is only heterotopic. I know this can be a little bit challenging, but if you keep looking at them and keep practicing, I think you guys are going to do amazingly. So let's do a couple practice problems. In all of these examples, we're going to go through, and I have already labeled HA and HB, and all we're going to do is identify what their relationship would be. For all of them, the answer choices are going to be homotopic, heterotopic, enantiotopic, or diastereotopic. And remember, some of them may have more than one correct answer. So if something is enantiotopic, as we said, it is also technically homotopic, because enantiotopic is a subcategory of homotopic. But I want you to use the best possible answer. That being said, let's go through each one of these. In our first example, we have a line of symmetry down the middle, which may not look important at first glance, but the reason I point that out is because this carbon right here is not a potential chiral center. And that is because this group and this group are exactly the same. Therefore, the relationship for number 1 is going to be just homotopic. They're exactly the same. For number 2, we no longer have a line of symmetry because of this methyl group hanging out right here. First thing I want you guys to notice is this is a chiral center. And in addition, this, oh, excuse me, I don't know what's happening. And this is a potential chiral center. So, the first thing I hope you guys think of is that I'm tricking you. Okay, that may have been really lame, but the reason I do that is because oftentimes students will see this wedge and they're like, oh, cool, chiral center. But just remember, they have to be unique. Just because he gives you a wedge doesn't mean anything. Wedge and dash do not inherently mean chirality. In addition, even if you were thinking that that's a chiral center, these two are what you're looking at. The relationship between those two is going to be heterotopic and nothing else. And the reason for that is you have two completely different hydrogens on completely different carbons. HA is on a carbon that's attached to 2 carbons and 1 hydrogen, and HB is attached to a carbon that is attached to 3 other carbons, completely different. For the third example, we have a double bond, but again, just like I tried to trick you with the chirality, this double bond is just a trick, because in order for the double bond to matter in these kind of problems, is if the hydrogens in question are on the double bond. In this case, they are not. So pretend the double bond doesn't even exist. Only thing you need to notice is that this is a potential chiral center. So HA and HB would be enantiotopic. Excuse me. I have the hiccups. Enantiotopic. Next up, in this case, we really do have a chiral center right here. Yay! All right, this is indeed a potential chiral center. So we know if we have a chiral center present and we have 2 hydrogens in question that are on a potential chiral center, they are going to be diastereo. And I'm not going to write the whole word because it just gets ugly. Next row, we have another double bond, and now actually HA and HB are both on the double bond. Next thing we have to look at is cut it down the middle. Are there 2 different groups? Yes. Are HA and HB on the same carbon? Yes. So that would mean they are diastereo. We have a double bond again, because I want to drill that into your brains, right? So first of all, not only are HA and HB not on the same carbon of the double bond, they're not even both on the double bond. So they are just completely different, heterotopic. Next up, this is essentially the example we did before. This has a line of symmetry right here, but that's not even what we're going to focus on. So I'm going to erase that. What I want to focus on is the fact that this is a potential chiral center because these 2 groups are different. And that means, since there is no other chiral center present, these are enantiotopic. Last but certainly not least, of course, I had to give you another double bond, so we're going to cut it in half. And first thing we should notice is that these 2 groups are symmetrical. Therefore, this has to be homotopic.